sure you get through that. There's one problem in MATLAB. Come see me if you have MATLAB questions. You got to write a function, so hopefully you sort of remember how to do that. If you took ME190 with me, you know how to write a function, okay? You better know. All right? Right, Caleb? Right. All right. So today, let's talk about what we're going to do. Today is the curved beam and bending lab. So I've uploaded some materials to Blackboard, and hopefully you've had a chance to take a look at those. The materials would be the handout for this particular lab, the lecture notes associated with this particular topic, and also a link to the video for the actual experimental portion of the lab. So this is going to go kind of like the combined loading lab last time, where we have some theory on the front end, and then you watch the video sort of on the back end to get the information. Then you write your lab report, and the world is good. All right. So unlike the combined loading lab, we have not had any theory related to curved beams and bending yet. So we actually have more lecture than normal for the lab period today. I would say the lecture is probably going to go an hour or maybe a little over an hour. Fortunately, the experimental video for this particular lab is only about 7 minutes. So the experimental portion is actually quite short. So that's kind of what's going to happen today. We're going to lecture for maybe about an hour, a little over an hour. And then I will set you free and you can watch the video for the lab. Okay, so with that said, let's talk about the experiment today. I'm going to bring up the lab handout and share that with you guys on my screen here. And if you haven't already taken a look at this, I would urge you to do so and kind of follow along with me now. So I'm going to share my screen. Okay, let me get rid of this crap. Okay. So today, what we're going to do is we're going to do an experiment on a curved beam that we put into bending. And so the curved beam that we're going to use looks something like this, and I actually have it here. So this is the curved beam that we're going to use for the lab. I show this picture here. I'll bring you guys into my full view so you can actually see the apparatus quickly. Okay, so here's the curved beam that we're going to be using for this lab. Notice it's got a pin here and a pin here. And the idea here is that this beam is already sort of curved, right? It's got this like horseshoe sort of shape. And the analysis for the stress in beams that look like this, which are sort of already have sort of this level of curvature, is a little bit more complicated and a little bit more, involved than some of the analysis that you've done for straight beams. And that's more or less what we're going to talk about in the lecture portion today. But I did want to show you this bar that gets used in the lab period first so that you sort of see it. So the idea here is we put it in a load frame and we compress down on either one of these sides, and that's going to induce some stress states in the bar over in this general area. Specifically, when we like compress this, there's going to be like compression on this side and tension on this side of the bar. We're really going to be looking at what would be like this cross section more or less of the bar and what's happening there as we load it sort of over on this side over here, right? So that's what's happening. Now, just like the combined loading lab, we have a series of strain gauges on this particular bar that are going to give you information about what's actually happening in the experiment. So if you'll notice, there are some critical points of interest on this bar, specifically like this inner edge right here and the outer edge right here. Those are two pretty important points for us and points that are going to sort of have like the maximum stress in this particular member. And that just sort of makes sense intuitively if you've thought about like just compressing this horseshoe generally. All right, so those 2 points here and here, we label in this lab as here point A and here point B. And you'll notice, and I'll sort of show this here as best I can, there's 2 strain gauges at each one of those locations. So you see here there are 2 singular gauges on sort of the inner edge of this particular bar, and there are 2 strain gauges sort of on the outer edge of the bar. These are both singular gauges that will measure strain in sort of this like longitudinal direction or sort of like this up and down direction of the bar. Those gauges are like redundant. They should be giving about the same value for strain with the loading that we've got on this particular bar. Okay, so that's kind of the idea of what's going on in this particular lab. We're going to measure strain here, measure strain here. You can convert that to stress values using Hooke's law and the modulus of elasticity of this particular member. And then you're going to compare the experimental stress values that you get at these 2 points to theoretical curved beam and bending stress calculations that you will do. So that's kind of the purpose of this particular lab. All right, so let's go back to the handout and we'll talk about this. So here again is the picture of the handout. And what I'm showing here is this is sort of like this curved member. And on this inner edge here, you have this point A that has 2 strain gauges. And so we have A1 and A2. That's the labels we're going to use for the strain gauges that are on sort of the inside edge of this particular member, strain gauge A1 and A2. On the outside, we have 2 strain gauges on the outside here, which are B1 and B2. Okay, and so you saw those on the outer edge of the particular member. So the idea here, again, is we're going to get strain values at the inner edge and the outer edge, transform those strains into stresses that we have experimentally, and then compare those experimental values to theoretical values that you might get from curved beam and bending equations. Okay, so that's the general idea of what's happening in this particular lab. So those objectives are sort of described above. Calculate theoretical stress states at prescribed points in a curved beam under a known state of loading. That's what we're doing. Operate strain gauge rating equipment, yada yada. Utilize Hooke's law in conjunction with experimental strain readings to calculate experimental stress values. All right, transforming strain into stress experimentally, and so on and so forth. Okay, so you get the general idea of what we're going to do here, hopefully. Now, the caveat here is that the stress that you induce in curved beams is not just my over I like it is for straight beams. It's much more complicated. And so we have to go through some lecture material, some theoretical material, so that you understand the differences in calculating the stress inside of a curved beam versus the stress inside of a straight beam. So we'll get into those notes now, and we'll talk about those differences with a lecture here. So the notes here are going to follow somewhat loosely with the notes that I've uploaded on Blackboard. So if you want to go to Blackboard and sort of look at the notes that I have there, I'm going to follow along with that somewhat loosely. And the reason I'm doing relative loose following is because there's a lot more detail in the notes on Blackboard than what I'm going to cover right now. Okay, and that's just because if I were to cover everything in the notes right now, it would take 2 hours, and we just don't have that amount of time. Okay, so let's do sort of an abridged version of the lab lecture notes. And if you have more questions, take a look at those notes, and there's a lot more detail in those notes. Okay, so let's go ahead with the lecture portion now, and we'll talk about stress in curved beams and bending. And so the first thing we might want to do is kind of like define what we mean by a curved beam or a straight beam. So a straight beam is, you know, the typical straight member that you've kind of been familiar with using in your whole mechanics career. And so that might look something like, okay, if we were going to kind of picture it as a cylindrical, solid cylindrical component, okay, maybe it looks something like this. So this would be your typical straight beam. And you've seen analysis on this where we like put this into bending with some bending moment M. And the stress generally here is like my over I in this particular member. So you've seen this before 100 times. You've done this, you know, in the first couple of weeks of this class. All right, compare that to what would be a curved beam. Okay, in a curved beam, we already have curvature of the member before we put any bending moment on it. So that might look something like this. I'll do the best I can. Okay, we're here now. We might have like some cylindrical member, but it's got some curvature. All right, and usually we denote this curvature like by the variable rho somehow is like some curvature. All right, and so in this particular member, if we were to subject this to a bending moment, let's say M and equivalently M, all right, we would not have your theoretical stress equation to give us stress in this member. So here the stress is not my over I. It's something else. And we're going to go through the derivation today to show what that something else is. Okay? So we'll say it's a mystery until 1 hour from now when it's not a mystery. All right. So let's go through this process. And the first thing I want to do is I want to sort of jog your memory on where this guy came from for straight beams, right? Because that will help us with our derivation in the stress equation for curved beams. So first thing I want to talk about is how we derive stress in straight beams. And the way that we do this is we actually derive the strain and just multiply it by the modulus to get the stress. Okay, so what we're going to do is we're going to derive the strain at any particular portion of a straight bar, multiply it by the modulus. That'll give us your stress distribution, which you already know is my over I. So the point is, how did we get there and how do we arrive at my over I? Okay, well, let's go through the process here. So let's consider a straight beam. And let's just say it's, I don't know, some rectangular prism for now. It's kind of the simplest way to think about it. Doesn't necessarily have to be a rectangular prism, but we'll just sort of take it as that for now. All right. And let's say we want to know sort of the strain on this guy as it's subject to a bending moment. So we're going to put a bending moment on this guy. Let's say M. And I want to know what is the strain. Okay. I'm going to look at one differential element, one small slice of that bar. So let's look at a small little slice of that bar, which is sort of here. And let's say that this particular slice has some differential length dx. So get small slice, this like width dx. All right, so let's sort of blow that up, and we'll blow that up over here. Here's our element, and we'll say first in this undeformed condition. Here we are, we generally have this piece that's of width dx, right? Now let's say I'm interested in the strain in the x direction of any arbitrary point on this particular piece. So let's say I'm interested in strain at like this location, or what would be like this portion of the bar. What is the strain at that particular location? Okay, so what I want to do is I want to see how basically this particular portion of that rod deforms as I put a moment onto it. And so we understand that as you put a moment onto this guy, it's going to sort of strain and deform. And that deformed configuration, if we load it, might force it, and I'm kind of like exaggerating this here, to look something like this. This is obviously highly exaggerated, okay? All right. And here we have deformed with some bending moment applied that is M. All right. Here's like our point of interest up here. And so we want to know how basically this little width of the bar changes in length as we go from undeformed to deformed. That would be kind of like your strain measurement. All right. Okay, so let's do this. We notice that in this deformed condition here, sort of like bent this thing upwards, so now it has some sort of inherent curvature to it. And so if we thought about how these edges pointed back to some center of curvature, it might look like this, with some center of curvature at this O prime. Right? You would also agree with me that there is some portion of each one of these members that stays the same in its length, and that would be the neutral axis. So we know that, like, if we're putting this thing into bending, that there is some portion in the bar that does not change in length. So here, this is same length. And this is neutral axis. Playing is hard. All right. There's some portion that gets longer. That's like the bottom part here. There's some portion of the bar that gets shorter. That's like the top part of this bar here. And then there's some piece in the middle where you have this neutral axis. All right. We'll say that the distance from the center of curvature to that neutral axis is the distance rho. This is just a generally accepted radius of curvature. That's this distance here. We call this distance rho. We say this is the radius of curvature of this particular member. Okay. I also might want to define the distance that my point of interest is away from the neutral axis, and I can do that in both of these pictures. So here, this is the neutral axis in the undeformed case, and my point of interest is located at some distance away from that neutral axis, which I will call little y. Right? The distance between the neutral axis and that point of interest does not change in the deformed case. It is still the same length here. Okay, it's still that same length. So now if I want to know the strain at this point here, I want to know the change in length from this location to this location, right? So let's put some nomenclature to each one of these lengths. Let's say that this particular length here is the length ds, and this length here is the length ds prime. All right. So then strain is, it's the change in length divided by the original length. So the change in length is ds prime minus ds. It's my change in length divided by the original length, which is ds. Capiche? Okay. Now let's define each of these pieces. ds. All right, well here ds is the sort of original undeformed length, this guy here. All right. Notice that before I deform this, it has this original length dx, which is the same length as this portion of the bar at like the neutral axis. Okay. We notice that the neutral axis does not change in length from situation 1 to situation 2. So this particular length of the bar is the same as ds, and it's the same as what is listed over here. Okay. So in this deformed condition, this portion of the bar is ds. Got it? And we can see that this particular portion has a length that's given by this radius of curvature rho multiplied by the angle that's created here, which we typically call d theta. It's the angle sort of swept out by the curvature of this particular piece. So here we will say that ds is equal to the radius of curvature rho times d theta. Right? It's the original length at my point of interest. ds prime, I'll use a similar strategy here. I'll look at the deformed condition. So here's my ds prime. And now I'm going to do sort of this same like arc length of a semicircle calculation, except now my radius of curvature is not rho. My radius of curvature is rho minus this distance y. So ds prime is rho minus y d theta. Now I'm ready to calculate my strain. It's going to be the deformed length, rho minus y d theta, minus the original length, rho d theta, all over the original length, which is rho d theta. All right. We'll obviously see that like d thetas cancel out of this, yada, yada, yada. We'll see that this positive rho will cancel with this negative rho, so those guys will go away. And all that you're left with here is that the strain is negative y on rho. Okay. What does this mean? Okay, what is this an equation of? Okay, well, this is a linear equation. Okay, you may, if you want to think of it, write it as negative 1 on rho times y, where this is like the slope and this is like the variable. Okay, so this is in like slope-intercept form, right? So this is a linear equation. If we convert this to stress, you have stress is just the modulus times this, negative ey over rho, which is also linear. Okay, and you know this to be true from just your knowledge of what happens to a beam in bending. So if you look at like the side of a bar in bending, you know this to be true, that some bar undergoing bending has a distribution that looks like this. Okay, where this is your linear equation. Usually you've seen it as my over I, but here we write it as negative ey over rho with our derivation. All right, this is just a linear equation. The way that you get to the form that you know is through moment curvature relationships. Which looks like something like 1 on rho equals m over ei. Hopefully you talked about this in 2004. If not, I don't really have time to cover it right now. But if you make the substitution, 1 on rho is this guy into here, then you'll end up with what you know as stress is my over I, or negative my over I as the case may be. So this is how you actually derive your stress equation for bending. Maybe you went through this in 2004, probably you did not. Okay? This, again, I will emphasize, is a linear equation, right? Y is your variable, and negative m over I is your slope, right? And that's how we sort of define stress for a straight beam that's in bending. How are we doing? How are we liking the math magic today? We're math magical today. All right. Now we need to compare the derivation of a straight beam, which we just did, to the derivation of a curved beam to see how things differ. Okay? So now, same thing. but with curved beam. All right. Before we sort of dive in on that and do all of that, we have to define some terms of a curved beam. Right? We've got to define some variables here so that we're all kind of on the same page on the variables that we're going to see shortly. All right, so again, here's our curved beam. Okay, that's, again, not the best, but I'm doing the best I can. Great artiste skills. We have to define some things here. All right. This beam is undeformed in its current configuration. Okay, so we have to define some variables about it. Let's say here, this is our center of curvature again, O prime. Not to be confused with O pra. This is O prime. Right? We can define, like, let's say the distance to the inside edge as like capital R I. We can define the distance to the outside edge as capital R O. I think those things are pretty obvious and intuitive. We can define a length to the centroid of the cross section. So, if we sort of like sliced this beam here, and we looked at this, here's section AA. There's going to be some centroid of this cross section. Okay. And so the distance from O prime to that centroid, we label as R bar. Right? So that's going to be, here. Also in the cross section, you may have a point of interest that you care about, where you actually want to measure the strain. And so let's say your point of interest is up here on the bar, sort of this upper edge. Let's just say some arbitrary point. Okay. We define the distance from the center of curvature to that point of interest. Let's call this point P as the distance here, just little r. Okay. So let's put some writing to this. So R bar, this is distance from center of curvature to centroid of cross section. R, this is your distance from center of curvature to point of interest. We have what we call capital R. Distance from center of curvature to inner radius. RO. Similar idea, from center of curvature to outer radius. I think that's pretty intuitive. And we have one last thing that we want to define. And that last thing that we want to find is the location of the neutral axis on this cross-section. Now, that requires us to have good knowledge of what the neutral axis is. And remember, the neutral axis in a cross-section is the axis where we have zero stress and zero strain, right? So lastly, we have one more, which is RNA, which I have not drawn on the picture yet. This is distance from center of curvature to neutral axis of bending in the cross-section. For straight beams, the neutral axis and the centroidal axis are the same. For curved beams, they are not. And it is always true that the neutral axis location is shorter than the centroidal axis location. And we'll show this and talk about why this is in just a second. But for curved beams and bending, the location of the neutral axis is always slightly in from the location of the centroidal axis. So I'll give you a second here, and then I'm going to actually draw it on the picture. So here's our picture of our curved beam. And here is how we defined R bar. It's the distance to the centroid of this cross-section. The neutral axis is located slightly in from the centroidal axis. So the neutral axis in this particular cross-section might lie, let's say, right here. Okay. So then this distance here is RNA. The distance to the neutral axis, where here it is less than R bar. Always less than. All right. Good. We got those things out of the way. Let me leave this for just a second for those copying. How are we doing? Still awake? Get your coffee. Go get it. Right now. Wake up. All right. Let's now move on. We've got good definitions for what these things are. So we're ready now to sort of tackle the derivation of the strain for curved beams. So just like we did for straight beams, we're going to go through a derivation of the strain in some arbitrary element of a curved beam. And then we're going to multiply that by the modulus to get you the stress and look at what the stress distribution is. I will give you a little snippet here and that it is not linear. Okay, so, ooh, I'm giving you some like illusion here. Foreshadowing, they call it in writing or movies or whatever. All right, so now stress in a curved beam. All right, same idea. Is it will derive strain, then use Hooke's law to get the stress. And we'll see what the distribution is. It will not be linear. You're going to be blown away. Blown away, I say. Just like that. All right, so let's look at a curved beam and what we're going to do here. So remember a curved beam? We've got this going on, and we're going to look at just like one section of that curved beam. Right? Just like before. All right. So let's blow that bad boy up and leave yourself some space on the paper, make this picture nice and big. So we're going to put a lot of stuff on here. All right. If we look at one little element here, I'm making this nice and big. This is an element that we might have in our curved bar before any deformation has even occurred. Okay, we already have this curved looking thing because just of the general curvature of the bar. So here this is undeformed. Okay, so this guy, undeformed condition, already sort of like points back to some center of curvature down here. I don't know if I can fit it in. I can fit it in. Come on. At O prime. All right, it's already got that sort of curvature associated with it. All right. When we put a bending moment onto this thing, it is going to deform even further. So now let's put a bending moment on. This thing is now going to deform even further. And it's going to deform to look something like this. Again, highly exaggerated. Okay, and then this is your deformed condition. Notice that there is one portion of this particular, element that does not deform in shape, and that would be this fiber of the particular bar, which is right here. This portion that does not deform, this is the neutral axis. Okay, so let's go ahead and use sort of the definitions that we've already talked about to define that distance from O prime to that location. Well, it's pretty obvious from our definitions that from O prime to that location is R and A. It's how we sort of defined the distance to the neutral axis, R and A. Not to be confused with ribonucleic acid. This ain't a biology class, homies. All right. Okay, now let's say that we have a point of interest on our bar that we care about, and let's say that that point is here. This is our point of interest. Let's call it point P. Right? We want to know what the strain is in that particular point as it goes from undeformed to deformed. All right, well, the original length, I think that's pretty easy to see, is here. And so this original length we'll call ds. And as we put a bending moment onto this, this deforms it into a longer length, and we're going to call that ds prime. That longer length includes this extra little bit on the sides. Okay. So here we have ds prime. It's this deformed condition at the point of interest. We said that the length from our center of curvature to the point of interest, so that's O prime to P, is the distance R. Sorry, not R bar, it's just R. Okay. A couple other things we're going to define is the curvature of this bar has some original angle already associated with it. And that original curvature would be like this curvature here, this angle. This angle here is d theta. It's the original sort of curvature angle of the undeformed piece. And one other thing that we're going to define is the angle that's created between the original piece and the deformed piece. And that is this angle here. And that angle there is two parts of a whole angle. We see both of them occurring on opposite sides. And this is going to be delta theta on 2. Same over here. Okay, a lot going on in this figure. Complicated, I know. But I think we're finally ready to tackle our strain calculation. So at point P, strain is the original length minus the deformed length over the original length. All right. The original length ds is again given by that arc formula for a semicircle. Here that's going to be r d theta. Okay. It's this r times d theta. That is this original length ds. ds prime here is that original length ds plus the additional bits on the sides here and here. Okay? So ds prime is going to be the original bit, which is ds, plus those bits that get added on the sides, like this guy. All right? Well, the equation for that is, again, we're going to use like the arc equation of a circle, where here the radius of curvature is this length to get to this point, if this is like our origin. And the angle that we sweep through is this angle d theta on 2. Okay. So again, an arc length, where this length here is RNA minus R, and our angle that we sweep through is delta theta on 2. So this is, we have 2 of them on either side of the element. We have our radius of curvature to that location, which is RNA minus R. That is this length here, multiplied by the angle that we sweep through, which is delta theta on 2. Complicated. Good. All right. So ds prime, this is r d theta, just from ds, plus the 2's will cancel here and here, and you're left with RNA minus R delta theta on 2. All right, who's stressed out? I'm stressed.
I thought the 2's would cancel.
Oh, yeah, thank you. I'm stressed, see? 2's cancel. Thank you. Okay. So finally, my strain. My original length minus my deformed length on 2. Sorry, not on 2. My deformed length minus my original length is going to look something like r d theta. Sorry, I got this backwards. It's final minus original. Gosh, tough morning. All right, that's a little bit better. Here we're going to have our expression for the final length, which is r d theta plus neutral axis location minus r delta theta, all minus the original length, which is r d theta, all over the original length, which is r d theta. Okay. This r d theta will cancel with this r d theta, and we'll be left with RNA minus r delta theta on r d theta. Let's replace this strange looking delta theta on d theta with a constant for now. We'll let k equals delta theta on d theta, and we'll come back to that later. And so we'll say then that the strain is k times RNA minus r on r. Hooke's law will get us that the stress at this particular location is the modulus times this constant k RNA minus r over r. It's a pirate's favorite, r. And here is your stress distribution in a curved member. Is this a linear equation? Ich don't think so, as the Germans would say. All right. This is a hyperbolic equation, not a linear equation. All right. So for a straight beam, you had a linear equation. For a curved beam, you have this hyperbolic equation. So what does this stress distribution actually look like if we were to sort of like look on the bar from the side for a bar that's in bending? Well, the picture from the side, here's our curved bar. All right. If we put a bending moment onto this, then our distribution of the stress is not linear. This is not correct. All right, as you might see with a straight beam. The distribution actually has this hyperbolic look to it. And this hyperbolic look is something like this. Okay. Here is your stress, which is E K R N A minus R on R. your hyperbolic stress distribution. All right. Whew, exciting stuff. Much different than the distribution that you see for straight beams, where if you were to assume, like, what does the distribution look like in a straight beam, maybe you would assume that it looks something like that. And man, would you be wrong. All right. Especially at like this inner fiber here, you would be way wrong. All right. Compared to your straight bar equation. Or what we wrote as pi over rho. Right? So there you go. So differences of the two. If you were to use straight beam equations for a curved bar, you would have significant errors. If you were to use curved beam equations for a straight bar, you'd probably have significant errors. So important to use the proper equations. All right. So this form is still a little funky here. All right. And there should be some questions that generally come up when you see that equation, like what is the value k, and how do we determine where the neutral axis is so that we can determine the value RNA? Those are some questions that you probably have when you look at this general equation. Okay, now let's talk about some of those things. And the first thing that we're going to tackle is, how do you determine the value of RNA? All right. Well, it may look a little complicated when you think about where or what you might have to do to approach this, but not really if you consider what like the stress distribution actually looks like. So up here we have our stress distribution here. And for this bar to be in equilibrium, this one here, then the amount of stress on the cross section and compression must be the same as the amount of stress on the cross section and tension. So what I mean by that is, more or less, the forces have to balance at that cross section, otherwise your pieces got to move to accommodate. So we're going to assume static conditions, and we're going to assume that the forces in that cross section all balance out to be zero. And what I mean by that is, the stresses on each individual differential area on that cross section, when you sum them all up over the cross section, got to be equal to zero. So we can write that in math language as forces on cross section must equal zero to be in equilibrium. Okay. So there is some location on that cross section where the hyperbolic distribution crosses from giving you compressive stress to giving you tensile stress. And we're going to enforce that the location where that distribution does that is such that the amount of compression and the amount of tension that you have on that bar equals out to be zero. All right, so the idea here is, where is this location such that the amount of material we have here and the amount of stress that we have here acting on that cross section balances out. We do that using calculus. So here, if we want sum of the forces on that cross section equal to 0, what we want is 0 equals the integral of all of the differential forces acting on that cross section equal to 0. An Arial integral on that cross section, adding up all the little contributions of all the forces on that cross section have to be equal to 0. So this is an Arial integral, a double integral on this cross section. All right, well, this can also be written in terms of the stress as the normal stress that's acting on that cross section, or we have a distribution for that. It's the stress on the cross section multiplied by the differential area over which we're acting. And we have an expression for this stress. That expression is E K R N A minus R on R dA. So this is what we're going to enforce here, equal to 0. This will tell us the location of the neutral axis. We'll note E and K are constants. So we can sort of pull them out since, it's all equal to 0, pull it out of the integral. 0 divided by a constant, still going to be 0. So then 0 is going to be equal to this integral over the area of R N A minus R for R dA. Okay. Let's rearrange this. Well, yeah, minus integral on A. We would have the second bit R divided by R, which is just 1 dA. First fundamental theorem of calculus. Whoa. And I'm missing that dA here, sorry. This distance to the neutral axis is a constant value. It's just some number, okay? So it can be pulled out of the integral. And we rearrange one more time. And find that the location of the neutral axis is simply the area divided by this wonky integral dA on R. This is the location of the neutral axis in the cross section. Where A is the cross-sectional area, and R and A we've defined before. This distance from center of curvature to the neutral axis. Okay. But what about this wonky integral dA on R nonsense? What about this stupid thing? All right. You could do that integral. That is not really that difficult of an integral. It's an Arial integral. You did some of these probably in 2002, some that looked a lot like this, ME 2002. Okay. Fortunately, this integral has been calculated for a variety of known cross-sections. Okay. This is given in your equation sheet, and it's also in the notes for the lab handout today. So this is what your equation sheet looks like. I'm going to pull it up quickly. Here, your curved beam and bending. Notice at the top here, you have like this term here is the area divided by integral dA on rho, or what we call dA on R. And then down here, you have a variety of different expressions that tell you what, depending on your cross-section, this area is, or this term dA on R is. All right, so hopefully we kind of see these here. I'll zoom in maybe a little bit on one in specific here. So for instance, if you have a rectangular cross-section and your center of curvature is sort of along this line, you would define the distance from the center of curvature to the inner portion of the cross-section as Ri, the distance from center of curvature to the outer portion of the cross-section as Ro, and then the width of that particular cross-section is B. That is very similar to what we have for this bar in our combined loading lab. All right, so you see we have this rectangular cross-section. There's a distance from the center of curvature to the inner radius we would call Ri, the outer radius we would call Ro, and then the thickness of this particular cross-section, which is here, we would call the distance B. So if that is your particular cross-section, then the integral dA on R, or what the equation sheet says is dA on rho, is B times the natural log of Ro on Ri. Okay? So your equation sheet gives you this integral dA on rho for a variety of different cross-sections. Trapezoidal, here's a circular one, here's an oval cross-section. You get the idea. There's also a table in your notes that shows this as well. And I'll bring that in here just for show. Okay. Not happy. There we go. All right. See the idea here? Again, rectangular cross-section. Here's the location of the center of curvature. And then we have a variety of different expressions here that satisfy this dA on R. Man, why can't I just drag this diagonally? Man, I have to like do it up and down and left and right. This thing's dumb. Terrible, I say. All right, I give up. You get the idea. It's in the notes. All right. Finally. We have to define that K term. All right. This one's a little bit outside the scope of what we can take care of right now. It's a little bit too long to sort of go through the derivation. If you're really interested, your book goes through the derivation. It's on Riley, the one of the two textbooks for the course, pages 451 and 452. And it goes through a lot of similar procedures as like the derivation of the moment curvature relationship for straight beams, though this one's slightly different than that. I'll kind of cut to the chase and give you the final form. The stress is the moment on the cross section multiplied by the location of the neutral axis minus the distance to the point of interest r, all divided by cross-sectional area A multiplied by r. It's again the distance from the center of curvature point of interest multiplied by r bar minus r and A. And this is your equation here for stress from bending in a curved beam. Very exciting. We have made it. Oh. Let's define these terms just so we're crystal. M is the applied moment, obviously. R and A is distance from center of curvature to the neutral axis. R is distance from center of curvature to point of interest. R bar is the distance from the center of curvature to centroid of cross section. A is cross-sectional area. And I think that just about does it. Complicated, man. Okay. Let's take 3-minute break. Go stretch your leg, get some coffee, whatever you got to do to get some sanity back. Go run a mile if you can run a mile in 3 minutes, world record. And we'll come back and we'll actually do some calculations with this equation specifically related to your lab. Okay? So 3-minute break. We'll come back at 11:14 on my clock. Okay, I'm back. Hopefully you're all still there too and not sleeping. I don't have any questions in the chat, so that's good. Anybody have any questions? 11:14. Welcome back to your favorite class. Ooh, hot coffee. Okay, let's go then, and let's look at your specific bar for this lab and what equations are going to be important for you. Okay, so away we go. And let's look at a very simple example. And the example is going to come right from the notes. So I'm just going to pull the notes up here and show you the example I'm talking about. And you can maybe copy this down in the meantime. So here's a sort of a CAD drawing of the curved beam that we're going to use for this particular lab. And we're going to load it up in that sort of fashion, right? We got those arrows that are providing sort of compressive forces at those pins. And we're going to derive what is the stress at points A and points B in this particular bar from that particular applied load. And we're going to do that using the straight beam equations, which is like your my over I, as well as your curved beam equations, which is like your m RNA minus R over A R bar minus RNA. Yeah, that's a mouthful. Okay, so let's do it. Okay, so with our example, the very crude drawing is this, very crude. Let me label this as P. Here's our point A of interest. Here's our point B. And what we're going to do is more or less slice through this guy at the location on the bar that contains point A and B. And we'll relocate forces and moments there, just like we do for combined loading, and see what stresses arise. So let's draw a picture of the half bar. After our cut. This is going to look something like this. Here, I'll take a lot more care with my drawing. All right. Okay. Here's my half bar after the cut. Here's the pin where we're going to provide our loading. In this situation, our loading is sort of in this downward direction, and I'm going to call this P. Now let's make some definitions of things that we kind of know what's happening here. All right, on the inner edge of this particular bar, this is point A. On the outer edge of the bar, this is point B. And remember, these are where your strain gauges are located for this particular lab. Let's define some of the things that we kind of already know. Here is the distance from the center of curvature of our beam O prime to the outer edge of this piece. This is capital RO, the outer edge, outer radius. Similarly, kind of to the inner edge here. This is capital RI. we might think about the projection of the cross section of this bar. So think of this as like a projected view. Okay. Or here, this is like the location of O prime. So again, if you're looking at this particular projected view, this would be the distance, capital R I. This would be the distance, capital R O. And this rectangular cross section has dimensions h by t. So here's the height h, and here's the thickness t. This cross section also has a centroidal location. Obviously, that's halfway through the cross section. It's here. It's the location of the centroid for this particular cross section. So the distance from here, this is O prime, to the centroid. This here is my variable little r bar, and I think that's pretty easy to see that little r bar is Ri plus Ro on h, or on 2. Sort of the average distance between the inner and the outer radius. You may consider kind of the neutral axis to sort of be running in the sort of the center of this guy all the way through. Okay, so that's the location, not the neutral axis, the centroidal axis. Kind of like running all the way through this cross section. Okay, now back to my my half bar up here. If I'm interested in this cross section here, I've got to relocate this force P to that cross section and also account for the moment that's created. So in this situation, I have to balance out the force with obviously a load P in the other direction. And I also have to balance out the moment that is created by relocating that force over there. And that would be the moment that looks something like this. If we let this length here be L, then the moment will simply be negative P times L plus R bar. All right. All right, we've got our free body diagram. All the right labels, all the right things at all the right places, as they sing in the song by I don't know who, because I'm not young anymore. All the right things in all the right places. I don't know who sings that, but they sing it better than me. Okay, we're ready. All right, in this cross section containing A and B, if you were to go about your standard business and use the straight beam equations incorrectly, I would add, you would have something like the stress in this cross section is a combination of the axial stress plus the bending stress, which for us would be something like P on A plus My over I. Yes? Don't forget about this compressive load that's happening P on A, all right? So if we're at, let's say point A, this is going to be something like the stress at A is equal to the load that's acting on the cross section containing point A. All right, so that's like this load P here, obviously providing us a compressive stress. I'll write this as a negative P on our area, which is H times T. It's the area of the cross section. And I'll add to it what we get from the bending moment. And I think it's pretty easy to see that this bending moment is going to provide compression at A. We think about kind of curling our sort of hand and providing extra compression at A. You might even just think about this by holding this bar like this and compressing this. You would envision extra compression from that bending moment on the inside fiber here. All right. So this is plus negative P times the moment arm, which we said was L plus R bar, multiplied by the location of A in the cross section, which is this variable Y. All right, well, the location here is this distance, which is H on 2. Times the area moment inertia in this cross section for a rectangle is 112 BH cubed, so 112 TH cubed. So at A, my general equation is going to be something like I can pull negative P on HT out of both of these. And you're going to have 1 plus 6 times L plus R bar, all on H. Okay. So there's your stress at point A if you're simply using the straight beam equations. At B, it's a very similar idea. Except that Y value now is negative H on 2 instead of at A it was positive H on 2. So here at B, similar idea, negative P on HT plus my negative M times L plus R bar times negative H on 2, so I'm kind of on the other side of the bar now, divided by 1/12 TH cubed. Again, I'll pull a negative P on HT out of both of these. Here I'll have now 1 minus 6 times L plus R bar, all on H. Okay, so this tells you the stress on the bar, the normal stress at points A and points B, if you're using straight beam equations. Remember, these straight beam equations are not the correct equations for actually calculating the stress for a curved bar. But in your lab, you're actually going to see and calculate the theoretical value using the straight beam equations here and see how far off they are from the real values. And you should see something of like 30% error, which is quite high. I told you you're going to have 30% error in your calculations and you're an engineer. Yikes. You're not a weatherman, okay? You don't get like, 70% chance to get it right and you still have a job, okay? It doesn't go that way. So that's straight beam equations. Let's look at now the curved beam equations. All right, it's the same idea. We're going to have the stress is some axial component plus your bending component. All right. And the axial component is still going to be the same. It's going to be something like negative P on HT but now the bending component is different, and we're going to utilize our new equation that we have for curved beams and bending. And that new equation here is plus m times, oh, I'm sorry, I made a mistake up here. This should be not m, but p. It's the load times the moment arm. Gives you the full moment. That's a mistake. Okay. Back to my bend. Here, this is the moment times RNA minus R bar. All over A times R times R bar minus RNA. All right. So now this here is the new equation that we have for curved beam. That's the stress that comes into a curved beam from an applied bending moment. All right, so let's look at points A and points B. At A, we've got to define our position R so that we can sort of punch it in here in this particular calculation. Okay. So back up to our picture. Here's point A. And remember, we defined little r as the distance from the center of curvature to our point of interest. Okay, the distance from the center of curvature to our point of interest A is simply the inner radius capital Ri. Okay, should not be a bar here, just a bar. All right, so let's do this. Stress at A. Again, this negative P on HT. I'm going to add to this my bending moment, which I know is negative P times L plus R. Plus R bar. It's my bending moment multiplied by RNA minus the location to point A, which is capital Ri, all divided by the area of the cross section, which is H times T, multiplied by my location of point A, which is Ri, multiplied by R bar minus RNA, which you see here. Okay, this is your equation for the normal stress at point A. Using your curved beam formulation. At B, this R is R outer. Will look very similar. Still have this compressive component. Still have the same bending moment. Still have the same neutral axis location. Here now we're going to subtract not Ri, but Ro, because that's where B is located. All divided by the cross-sectional area, HT, times location of point B, which is Ro. Here, R bar minus RA. And here's your equation for the normal stress on the cross-section at point B. Man, it took a while. Okay, I have summed these equations up for you on the very last slide of the notes for this particular lecture. So in Blackboard, the PowerPoint that I handed out, or I gave you, sums up all of these particular equations. I've derived them here so that you can kind of see them and see how we utilize these equations. But the actual equations that I kind of just wrote down are here. Here are your straight beam equations. Here are your curved beam equations based on the picture above, okay, and the derivation that we went through. So you'll calculate the stresses at these particular points, the theoretical stresses, using the straight beam and the curved beam equations. You will see how those theoretical stresses match up to the actual experimental values from the lab. So the remainder of the time, 15 minutes, is yours to, I would say, look over that lab handout in pretty good detail and then watch the 7-minute video of the lab experiment. I'll leave you here. Thanks for coming. Kind of long today, I know. I appreciate you guys sitting through it. I know it's this by far the longest lecture period of a lab that we're ever going to have. So thanks for sticking through it, and good luck. I'll be around office hours every day, 8 to 9:30 if you have questions. And your report for this particular lab will be due 1 week from today. No rough draft this time. It's all on you. All right. Good luck, guys.